So, welcome to our seminar. Our speaker today is Adam Fuller, and his title, as you can see there, is Intermediate Subalgebras of Cartan Embeddings in Rings and in Sister Algebras. Please, Adam, go ahead.
Thank you so much. And thanks for inviting me to give this talk. So this is joint work with John Brown, who's at University of Dayton, not far from me, and Lisa Clark, who's in New Zealand at Victoria University in Wellington. Let me start with just some of the kind of big picture problem and some examples of this that I like and that have motivated me. So the vague problem I've been interested in a lot of different settings is if we have some operator or some algebra, I say operator or algebra here, but they won't all be operator algebras later. So just some algebra, and we have D inside A in some way. So it's some sort of inclusion. And we have something in the middle. Do we know anything about how D sits inside B? That's the motivating question here. And in particular, if the inclusion of D inside A, if this comes with some other data, does that data describe how D sits inside B? Yeah, that's very vague. Let me give examples of this and how this works. I think the most famous example, at least from an operator algebra viewpoint, is this work by Izumi, Longo, and Papa, building on earlier work by Choda, is that if M is a factor and we have a discrete group acting on M by outer automorphisms, then there's a one-to-one correspondence between the von Neumann algebras, which sit between M and this cross product, and the subgroups. So this is often referred to as a Galois correspondence. It's the subgroups of gamma give you the sub-von Neumann algebras in between M and the cross product. On the C-star algebra side, there's a similar result due to Cameron Smith, 2014. They showed if A was a unital simple C-star algebra and gamma was a discrete group acting by outer automorphisms, then again we have this one-to-one correspondence between the subgroups and the intermediate, C-star algebras between them. This is a series of 3 papers Cameron Smith wrote. They wrote 2 in similar problems in von Neumann algebras, generalizing the earlier paper by Izumi, Longo, and Papa, and then this last paper in C-star algebras. Really lovely series of 3 papers, which I read and have been rereading and citing for the last, 11 years, it seems. More on the C-star algebra side is a result by I wrote with Brown, Excel, Pitts, and Reznikov, and Kennedy and Ursu, generalized. If we have a discrete group with the approximation property acting on a unital C-star algebra, then if A is abelian and our action is free, or if A is not abelian, the correct, in this case, analog of freeness is pointwise residual property outer, which I won't get into because it's not going to come up in the talk. Then we have a one-to-one correspondence between intermediate algebras, and not the subgroups, but subactions of gamma. So Kennedy and Ursu wrote this in terms of subactions. In my paper here, we talked about sub groupoids. I'll get more into groupoids later. But essentially, this deals with the other extreme away from simplicity. So either abelian or when you have this other type of action. In the C-star algebra case, cross products. Away from cross products, there is similar results when you think of Cartan inclusions. For von Neumann algebras, a maximal abelian subalgebra D is Cartan if it is regular, meaning that the unitaries which normalize D, i.e. send D back to itself, if these are dense in M, and there is a faithful normal conditional expectation onto M. This is what's called Cartan. Being maximal abelian, being regular, and being in the range of a conditional expectation are all essentially saying D is big inside M, and if it satisfies all three, it must be very big. In this setting, Aoi in 2003 proved that when we have a Cartan inclusion, if ever we have a von Neumann algebra between D and M, then D will be Cartan inside M. And in terms of a Galois-like correspondence, so in terms of the data that you get in inclusion here, again, it can be described. Feldman and Moore, in seminal work in the late 70s, gave a complete characterization of Cartan inclusions in terms of measured equivalence relations. Aoi's result gives these intermediate subalgebras are in one-to-one correspondence with sub-equivalence relations. If you can't get your head around measure equivalence relations, which I'm not sure is a problem for many people, but it's a huge problem for me, these can also be described in terms of extensions of inverse semigroups, and in which case the one-to-one correspondence comes from sub-inverse semigroups from your initial data. This is based on a paper that I wrote with Alan Dontig and David Pitts several years ago. This approach also easier goes into non-separable von Neumann algebras than the measured equivalence relations. This could also be described in terms of groupoids instead of inverse semigroups. Most things, groupoids and inverse semigroups, you can describe either or. Renault has a recent paper where he looks at this in terms of groupoids. So that's the von Neumann algebra case. Everything Cartan works real nicely. In terms of the Izumi Longo Popa paper, where they showed that they had this cross product, this was a factor. This kind of gives the other extreme, because an example of a Cartan inclusion is a free action L infinity inside its cross product. If we have a free action, or no, I'm forgetting the adjective for von Neumann algebras, but the almost free action, then you get a Cartan inclusion. So this gives an example of a Galois type correspondence for abelian inclusion, but it's not based on the subgroup, it's based on finer data. The C-star algebra side of this problem is a little bit more complicated. So there is a generalization of a Cartan inclusion in C-star algebras, and these have been studied in a lot of detail since the mid-80s. The analog of a C-star Cartan inclusion is we have a maximal abelian subalgebra as before. We want D and A to share an approximate unit. They shared an identity before, so if it's unital, they'll share an identity in the von Neumann case. The regularity condition for the von Neumann case was that the normalizing unitaries were dense, or spanned a dense subset. In C-star algebra setting, you don't want to rely on unitaries because they're not usually as many. So here we just have normalizing elements without a restriction to unitaries. We want these to be dense, and we have a faithful conditional expectation. We don't need the normality condition because we're no longer in von Neumann setting, but we still need a faithful conditional expectation. So this is what Renault calls a Cartan inclusion. if you have the extra condition that every faithful state on D extends uniquely to A, this is what we call a C-star diagonal. This is due to Kumjian. Kumjian and Ben Renault gave an analog of the Feldman-Moore description of Cartan inclusions. So Feldman-Moore for von Neumann algebras gave this measured equivalence relation description of Cartan inclusions. In the C-star algebra setting, there is a groupoid description where whenever you have a Cartan inclusion, your bigger algebra is a reduced C-star algebra of a groupoid, and your smaller algebra is the abelian algebra on the units. I'll be going into more details about what groupoids are later if you're not familiar, but just to say here, there is a description. So you can ask then the question of if I have a Cartan inclusion and I have something in between, is this in here Cartan? And the Norman algebra setting, the answer was yes, due to OE. But it's more difficult here. So this was a problem looked at by myself, Excel, Pitts, and Resnikov. We showed that if we have a D inside A of Cartan inclusion, and if we have an algebra in between them, with the additional property, so C-star algebra in between, with the additional property that we are in the range of a conditional expectation, then we're Cartan. And in terms of a Galois correspondence, the intermediate algebras of these form, which are in the range of conditional expectation, are in one-to-one correspondence with the subgroupoids, which are both closed and open in the topology. In the von Neumann algebra setting, any intermediate algebra is automatically in the range of a conditional expectation. So that is one clue as why things were more difficult here. To get a stronger result and get a full Galois correspondence, we needed some extra conditions. Firstly, we need to assume A is a nuclear C-star algebra. And secondly, that D is a C-star diagonal. So in this setting, so C-star diagonal again is when we have a Cartan inclusion with the unique extension property of these states. In this setting, whenever we have an intermediate algebra, it'll also be a C-star diagonal. And in this case, the Galois type correspondence is between the intermediate algebras and any open subgroupoid. So this was where I was at. Obviously, I'd been working with John Brown. John Brown and Lisa Clark had worked together. Sorry.
Sorry to bother you, but so the difference between the two theorems is that, I mean, with more hypotheses, you get the intermediate algebras you account for are the ones that are not just Cartan, but diagonal.
Yes.
Right?
Yes.
Yeah, but then what surprises me is that the condition on the subgroupoid is less stringent than the condition that you have above for general Cartan subalgebras.
Yes. So
why? I mean,
so the Clopin condition is what gives you the closed condition is what gives you a conditional expectation. There's two things, and there's two things at play here. Being a C-star diagonal gives a concrete description of your conditional expectation from A to D in terms of normalizers. It is take the closed convex, so take the closed convex hull of U star, where U are unitaries in D. This will give us the conditional expectation. So we have this concrete description of the conditional expectation in a C-star diagonal case. This is due to Archibald Bunce Gregson studied the unique expectation property in the early 80s. This allows us to, whenever we have a having an intermediate algebra, the difficulty is knowing whether or not you're regular. D will be maximal abelian in it. There will be a conditional expectation by restricting. It's the regularity condition which is difficult. This concrete description of the conditional expectation means that we can recover normalizers in B. We can find normalizers in B. And the nuclearity condition means that we can completely describe something by its normalizers. This is a amenability condition.
But if in the first theorem the hypothesis of the second are satisfied, right? Don't you get
Right.
an equivalence between? So
Yes. So anything in here, if there is a faithful conditional expectation from A to B, then the H will be Kloben.
okay.
Yeah. But this allows us to look at ones which are also that aren't also in the range. Worth noting that these conditions are sufficient and mostly necessary, and I'll talk about how necessary as I go. But we have an example of well, we have many examples of nuclear C-star algebras with Cartan inclusions where this theorem does not hold.
Okay.
So the C-star diagonal condition is to some extent mostly necessary, and I'll talk exactly how necessary later. But
Okay. Thank you.
This was the state of the art when myself, John, and Lisa started looking at this problem. So John and Lisa had worked a lot in Steinberg algebras. I was Steinberg algebra curious. So I, asked them if they were interested in looking at this further, and they'd actually already been talking about it. So we joined forces to look at a similar problem for Steinberg algebras. So let me get into the meat of my talk and introduce the main topics being Steinberg algebras. Firstly, a groupoid is a small category with objects G0, which we'll call units. So you can think of it as just a set, G0 being a set of things, and the groupoid is arrows between them. So we have range and source maps, and we have composition wherever we can. We have two. I have gamma and sigma. Then I can look at the product of gamma and sigma. I have the map from here to here. Satisfy some conditions. The source of the composition is where you started. The range of the composition is where you end. For units, i.e. the objects, source and range are just themselves. And we can always compose an element by a unit on either side, that element being the source of gamma on the right, the range of gamma on the left. And we always have inverses. So this is called a groupoid. It's a if we have a single unit, if there was only one unit, this would be a group. When there's more than one unit, you have a groupoid. I'll give an example in a minute of more kind of useful example that's not a group. Some other things that we want with our groupoids is a topological structure. So it's a topological groupoid if there's a topology on our groupoid G with inversion and multiplication being continuous. So same as definition of topological group. A groupoid is etale if the range and source maps are local homeomorphisms, meaning around every point there is some set so that my range map going into the units is a homeomorphism. And actually, I say range and source, but one implies the other actually. Etale groupoids are analogous to discrete groups. If you have an etale groupoid and I fix a unit and I look at its isotropy being all the gammas which have range and source equal to x, so all the points which are loops. Being etale means that this will be a group because we can always compose things, but it'll be a discrete group when we're etale. So etale is the analog of a discrete group. We don't want to look at a discrete groupoid, that's too discrete. Another way to describe etale is if there's a basis for the topology. Sorry.
Bisections, right?
Yes. There's a basis for topology of bisections. So element of these subsets, these open subsets where the source and range are homeomorphisms. If in addition, this basis can be compact open bisections, we call it ample. In the C-star algebra literature, generally you want to look at, or the stuff I've been talking to up to now have been Hausdorff etale groupoids. Actually, I haven't even used the word Hausdorff. Everything I look at will be Hausdorff here. In C-star algebra literature, you can use this. In the algebra literature, you want the extra addition of ample. Some examples of ample groupoids. If I take a Cantor set and I have a discrete group acting on X by homeomorphisms, then I can form the transformation group where the source of a pair X gamma is just where it starts. The range is where gamma sends X. Composition is defined when if sigma sends Y to sigma Y, then gamma sends sigma Y to gamma sigma Y. And then the inverse is this here. This makes it a groupoid. If we put the product topology, so gamma being discrete and X being the Cantor set, with the product topology, this becomes an ample groupoid. If I just had a compact Hausdorff space here, then this would be etale. It's the totally disconnected nature of the Cantor set, which makes it ample. Another
Why compact? Wouldn't locally compact?
Oh yes, yeah, locally compact too. Yeah, everything works here non-unital. Another example comes from graph algebras or graphs. If I have a directed graph and I look at its infinite paths, I say they're shift equivalent if after a certain point they're equivalent. And then I look at all of these pairs where X and Y are equivalent by a shift of K. And I can make that into a groupoid with following properties. Source of X, K, Y is X, range is Y. I can compose them when I have the same element here, in which case, sorry, this should be X over here. In which case I have the composition is K plus L, XZ. And you can see that there's a transitive. If X is shift equivalent to Y and Y is shift equivalent to Z, then X is going to be shift equivalent to Z with, I'm talking in Argentina. I can go back and speak. If X is shift equivalent to Z, then we can, it'll be by K plus L. And then the inverse, we swap border and we do minus K. This is a groupoid structure, not hard to see. A topology on this is given what's called cylinder sets, where we take any two paths, alpha and beta, which start at the same place, then I can add an infinite path to them. And this gives me a basis for a topology. With this topology, this will be ample. So if you're not used to groupoids, but you are familiar with either groupoid C-star algebras or Levitt path algebras, any groupoid, any graph C-star algebra is a groupoid C-star algebra with this groupoid. Any Levitt path algebra is a Steinberg algebra with this groupoid. So this is the groupoid which describes those things. Okay, a Steinberg algebra. If we have a ample groupoid over and we have a ring, the Steinberg algebra is defined to be the locally constant functions into the ring. And we put a multiplication on this by convolution, and this gives us an algebra structure. And this is called the Steinberg algebra. So this is, again, if you're used to the C-star setting, you look at compactly supported functions, compactly supported continuous functions into the ring, into your ring being C, and you have the same convolution. Another way to describe the Steinberg algebra is this locally constant condition will mean that any element is a linear combination of just the characteristic functions on bisections. And the multiplication here would be just the product of the sets. So where that product exists. So this is a very useful description of the elements of Steinberg algebra, which you don't have in the C-star algebra setting. So Steinberg algebra is just a bit of history. These were introduced originally by Ben Steinberg and ran with a paper by Clark, Tomford, Farthing, Sims. They are the ones who named them Steinberg algebras after this work by Ben Steinberg. As with C-star algebras, there is a notion of a twist of a groupoid, an algebraic twist rather than a topological twist. And you can define Steinberg algebras in that setting. The definition of a twist will take 3 slides, and I think we'd kind of get bogged down in too much in it. But this stuff also works in the twist setting, and there's a paper by Armstrong, Clark, Courtney, Lynn, McCormick, and Ramage, which develops that theory. And there will be twists appearing later, but I'm just going to kind of hide the details because in all our results, even when there is a twist over G, it is the properties of G which will matter to us here. Okay, so now I want to define what it means, the types of inclusion. So the idea of what if the analogs of a Cartan inclusion in this setting. For that, we need just a couple of properties. If I have an algebra over a ring and I have an abelian subalgebra with idempotence ID, we say the idempotents are local units if whenever I have a subset in A, then there's an idempotent, a finite subset, there's an idempotent which acts like a unit for that subset. This is analogous to having a shared identity or having a shared approximate unit. There's also an analog of a normalizer. A normalizer for in A for D, n is a normalizer if there's an element n dagger, so that n dagger n is equal to n, and n dagger n, and well, this here, and these two elements together map back into D. I say this n dagger is necessarily unique. That is a theorem. That is something that needs to be proved. But if you have a normalizer, if you're a normalizer, there's a unique element which satisfies this, which justifies this n dagger notation. Note that this is not the same as like the adjoint of a C-star algebra. The C-star algebra. This is more akin to a normalizing partial isometry. If you're normalizing partial isometry, the adjoint will also satisfy this. In the von Neumann setting, when I defined Cartan earlier, I did it in terms of normalizing unitaries. That is equivalent to defining it in terms of normalizing partial isometries. Unitaries are, of course, partial isometries, but if you if the normalizing partial isometries span weak star dense subsets, then you can get away with just unitaries. So this is in some ways more like the von Neumann definition.
One question.
Yes.
So suppose your algebra A is a groupoid algebra, and say you take it over the complex numbers. So this has an involution as an
Yes.
algebra. So and you take as D the Steinberg algebra of the unit space. Then the dagger is the star, right?
Yes,
or not?
for the normalizing for the normalizing bisections. For the
Yeah,
bisections, it's true.
yeah, but these reconstruction theorems, right? That you have a Cartan subalgebra and then you recover the groupoid and so on. So do they imply in some way that that the algebra has an involution and that the dagger in the end will turn out to be the involution?
No, not necessarily. I don't
Uh-huh.
think. I don't think so. I think it can be different, though I'm not certain on that.
Okay. But if you suppose your object of study were not the plain algebras, but the algebras with an involution, then you might require the dagger.
Yes, so that might be something you want to oppose upon, because this is I mean, this is a more Penrose inverse, and you'd want your adjoint to behave like that.
I think in this circumstance, like that Willie's describing, that it isn't necessarily like the adjoint would work in the complex numbers, but you don't necessarily want to, or it's not the only thing that would satisfy this. For instance, if n and n dagger were just functions on the unit space and n is constant 2 and n dagger is constant half, then n dagger n is equal to 2. But
Right.
2 is obviously not the 2 adjoint, or the complex conjugate of 2 is not a half.
Right.
Yeah, because not everything is as norm 1, so to speak.
Exactly.
Thanks.
Yes, sorry, thank you, brother. So we're going to say its inclusion's regular if, well, the normalizers are big in A, like before, and we also want that there's lots of idempotents in D. I mean, this isn't going to work if there isn't lots of idempotents. We can also look at the idea of conditional expectation. So conditional expectation, I just wrote conditional expectation, but this will be a map from A to D, which is the identity on D and is a bimodule map. This will be how it's defined. If we are a regular inclusion, we'll say it's faithful if E and A is equal to 0 for every single normalizer, then A is equal to 0. So this allows us to describe a faithfulness in the absence of an adjoint.
So does this imply that I mean this you're preferring the left to the right in the definition?
Oh yes, I am.
So does it imply that it also holds the other way or not?
I think so, and I'm. Yes, I think it does, but I'm.
Yeah, so some properties of the normalizer must be in play, right?
Yes, I think that's happening because we can write A as a span of normalizers and then move things around then. And then we say it's implemented by idempotence if it is really just a compression by projection. For each element, there is an E, so it's not the same projection always, but we can always write it this way. This allows us to give our definitions of the generalization of being Cartan, and there's 3 here. So we're going to say we have a regular inclusion, we have a faithful conditional expectation. D's without torsion over R is another condition needed, which this is saying that if lambda E is equal to 0 for E and normal E non-zero projection, then lambda is equal to 0. So we can't multiply on the idempotence by the ring and get 0. In this case, we say we're algebraically diagonal if the what are called free normalizers. So the normalizers which square to 0 are a dense subset of A. The definition of C star diagonal I gave earlier in terms of unique extensions of states can also be given in terms of dense normalizers that satisfy this. So this is an algebraic analog without having to talk about states. We are algebraic. Sorry.
What does density mean in the purely algebraic setting?
Oh, it means I forgot to write. It means I keep forgetting that I'm in an algebra, not a C-star algebra. Yes, dense means is. So yes, it spans it spans A.
Spans the whole thing.
Yes, yeah, because there's no closures here, so that's a bad habit on my part. Something John and Lisa were constantly correcting on me. We're Cartan if we're maximal abelian, and we are what's called quasi-Cartan if E is implemented by idempotency. And this is something which doesn't quite have the direct analog in the C-star setting. We do have this chain of inclusions, but this is a theorem. This isn't an obvious statement. I don't have the names of people who prove this theorem on this slide. I will have it on the next. And there's like a lot of them. So the question then is, when we have this inclusion of if we have a quasi-Cartan conclusion or a Cartan conclusion or a diagonal inclusion, do we have this intermediate algebra results? First thing to note is that we do have an analog to the Kumjian-Renaud descriptions. We have that whenever we have a quasi-Cartan inclusion, then we have a groupoid description. It's actually a twist, which I've just written in terms of the groupoid. This is actually a twisted Steinberg algebra in general. But whenever we have a quasi-Cartan inclusion, there is a groupoid G or a twist over G, so that the larger algebra is the Steinberg algebra and the smaller algebra is the algebra over the units. And how this relates to the subthings, if firstly, if n is in a normalizer, then its support is a bisection. So the only normalizers are the ones coming from bisections. This is called the local bisection hypothesis. If we're diagonal, then G is principal. And if we are Cartan, then G is effective. Where principal here means that at any point in the unit space, the only elements that go from X to X is just X itself. So the isotropy group over X is just a singleton. And we're effective if we look at all the isotropy groups, the interior of that is just G naught. So there can be some non-trivial isotropy, but not too much. So this is analogous in the example of the action on a compact Hausdorff space. Principal would be from a free action, and effective would be a topologically free action. Okay, so now we can get to the actual. Oh, sorry, I didn't mention these people. This is a big work due to Armstrong, DeCastro, Clark, Courtney, Lynn, McCormick, Ramage, Sims, Steinberg, which I didn't write on the other slide because there wasn't enough room to write it. They proved these reconstruction theorems in this lovely paper where they go through a lot of detail of all the different things can happen. I'm told there was 2 groups working on it, found that they were working on the same thing. So that's one reason why there's so many people on this. So where myself, John, and Lisa came into this is we were interested again in the question of if we have D inside A being one of these types of inclusions, what do we know about an intermediate inclusion? And I'll go through, we get stronger results the more conditions we put on, same as the C-star setting. Firstly, for quasi-Cartan, we can't say a huge amount. We can say that if we have an intermediate algebra and we know that this inclusion is quasi-Cartan, then it comes from an open subgroupoid of H. So if you know that you do have the intermediate algebras preserving the quasi-Cartan property, then that's coming from a subgroupoid, and vice versa. Any open subgroupoid will give us a quasi-Cartan inclusion. But what we don't know is that if we just had this, and we didn't know that C was quasi-Cartan, there's no reason to think that it would be. And actually, in general, it won't be. Do I have an example of that? No, I have an example next thing. If I restrict myself to just Cartan, then we have the analogous result that we had in the C star setting. That if I have a Cartan inclusion, then whenever I have an intermediate algebra which is in the range of a conditional expectation, then I have a one-to-one correspondence between the intermediate algebra and the subgroupoids, which are both open and closed. So wide here means they contain the same units. So it's the subgroupoids in here, which are both open and closed. The open and closed condition is what gives us the conditional expectation. Sorry, the closed condition is what gives the conditional expectation. And the open condition allows us to embed the Steinberg algebra of H into the Steinberg algebra for G. So this is analogous to the C star conditions, almost, the same theorem. This does not hold in the quasi-Cartan condition case. So one example here is if I take the 3-element group and just take its Steinberg algebra over C, so this is just a group algebra, then this inclusion of C in here is quasi-Cartan, but not Cartan. This is not maximal abelian. And if I take, so delta naught, delta 1, delta 2 being the elements C3 inside this algebra, looking at this algebra here, where I'm not separating delta 1 and delta 2, but they're both present, then there is a conditional expectation from my larger algebra onto C, but C is not, this inclusion here is not quasi-Cartan. If I look at the support of C, because I can't separate delta 1 and delta 2, then I'm actually getting all of C3. So because I can't separate delta 1 and delta 2, then this is not going to be a regular inclusion. So quasi-Cartan in some ways is an algebraic analog of Cartan. When it comes to these intermediate results, you do need the Cartan. Next thing to ask, obviously, is about diagonal, because that's where we got our strongest results in the C star case. If we have a diagonal inclusion, let me just ignore this for a second. So let's just look at a one. If I have a diagonal inclusion, then I do have the one-to-one correspondence. Whenever I have an intermediate algebra and I have my open subgroupoid with the same units inside G, a one-to-one correspondence between intermediate Steinberg algebra and an open subgroupoid. C will be the Steinberg algebra for this H. This can actually be strengthened, however. We can have, so again, principal meant, so C star diagonal meant G was principal, meaning there was no isotropy. We can, however, have a little bit of isotropy. So these conditions here mean that if I have two elements U and V, two units U and V, and there is more than one, there's say a gamma and a sigma between U and V, then this means that U is equal to V. So gamma and sigma are like this. And in fact, the isotropy is 2. So this means that I only have one loop. I have U itself and just a single loop. So I can have isotropy as long as that isotropy is only an order 2 group. And in this case, I also have the one-to-one correspondence between the open subgroupoids and C. So this is a slightly stronger result than the C-star result, because the C-star result just had this, which led us to the question of, well, we didn't consider this in the C-star result. This question was much more natural to look at in the or at least for us in the algebraic setting. We were looking much more at the groups and what type of isotropy we got, which led us to this result, which was not what was happening in the C-star algebra paper, where we're looking at either has isotropy or does not have isotropy. But turns out this does work for the C-star algebra setting as well. So we strengthened that earlier result that if we have a groupoid with, again, either has no isotropy or has a tiny bit of isotropy, again, this only loops, only single loops, so only groups of order 2, and those ones are isolated, then any intermediate thing is Cartan. And we have the one-to-one correspondence between the subgroupoids and open subgroupoids and the intermediate algebras. So this is this gives examples which are not C-star diagonals, but we still have these intermediate algebra results. So yeah, this can be used to this strengthens this earlier result by myself, John, Ruixel, Pitts, and Rezenkov. I mentioned earlier a paper by Kendi and Ursu. They were looking at cross products of C-star algebras, not necessarily abelian C-star algebras. In that setting, they had also realized that groups of order 2 allow for these type of results. Okay, let me just say one more thing about this result here. One other thing we looked at in the paper was bimodules. So we looked at the linear subspaces in here, which multiplication on the left or right by elements in the functions in the unit space stay within inside M. So the linear spaces that satisfy this, we looked at the bimodules and whether or not these sets are determined by the groupoid G. Of course, intermediate algebras are an example of this. So this is a generalization of that. And this question goes back to work of Mouli, Saito, and Salel in the von Neumann algebra Cartan inclusion setting. In this setting, we have a theorem where open subsets of our groupoid give us the bimodules when G is principal. So we have a one-to-one correspondence between open subsets of our groupoid and the bimodules if G is principal. In particular, that does not hold here. The bimodule result does not hold with any isotropy. If there's any isotropy whatsoever, then the bimodule result will not hold. So if you want to get a full spectral theorem for bimodules equivalent for Steinberg algebras, you do need principal, or you do need a algebraic diagonal. Any amount of isotropy, even this tiny amount, will give you counterexamples. And I think I'm about time, so I'll finish there.
Thank you very much for a very nice talk. Are there questions from the audience? Yeah, Jono, please ask your question.
Hi, thanks for this lovely talk. I had a question about the second conditionalness theorem. So this seems extremely restrictive.
So which theorem?
The one right in front of us now, the condition
yes.
where we're allowed to consider slightly larger than principal groupoids, but the only things we're allowed to do is add on a disjoint union of Z2 as many times as we want, but it has to be separated from the rest of the groupoid. Is that correct?
It has to be separated from the rest of the isotropy. Like you could take -1 to 1. I'm not going to argue that it's not extremely restrictive. It definitely is. But you could flip this.
I see. Yeah. No,
and then you have 0 giving you being a fixed point. I mean, oh, okay, for Steinberg algebra, you'd want this to be 2 copies of the Cantor set. But anyway, 0 would be a fixed point. And so it's not separated from the unit space, but it is separated in isotropy.
All right, yeah.
But
Thanks for clarifying that. Yeah.
But yes, no, it is definitely a very restricted case. But it shows the limits. It precisely gives us the limits of where intermediate stuff falls down. And we were surprised that the answer was not isotropy. It was mostly isotropy.
I also have a follow-up question. Well, I guess it's not a follow-up. I have another question. Have you thought about pushing this flavor of results in the non-Hausdorff direction?
Yes. There is some things that you can do in the non-Hausdorff direction. Let me pull up on this. So this sort of result here, actually, if you know that you just say you have G being non-Hausdorff but topologically principal, and you know that this is topologically principal, then you can still say you can prove this result not just for the reduced C-star algebra but for the essential C-star algebra, because in the non-Hausdorff case, the reduced C-star algebra is not always what you want. There's another ideal that you sometimes want to quotient out by to get what's called the essential C-star algebra. You can prove that there. Beyond that, I don't have many. I'm sorry, let me just point out this was a student of mine called Ali Saleh. Was looking at that. Beyond that, I don't have a lot of. So I've looked mostly at C-star algebra. Let me say I have not looked at the Steinberg algebra situation. In the C-star algebra situation, it is difficult because non-Hausdorff means there is isotropy. So there's not going to be a C-star diagonal full result there, because you can always see the non-Hausdorffness at the isotropy, because the unit space won't be closed and the limit will give you an isotropy point. A limit outside of the unit space will give us something isotropy-ish. So you're not going to get a C-star diagonal or algebraic diagonal type results, or you would, but they're actually just Hausdorff. So there's barriers immediately, but I have not looked at the idea of if there is the non-Hausdorff isotropy is very small, like this restrictive condition, then maybe you can do something. But it seems that you wouldn't be able to do anything beyond this, is my expectation.
I mean, the other obstruction would be that you run into the problem that you have multiple subalgebra. Well, you have the same algebra can be modeled by multiple different subgroupoids.
Yes.
For the essential.
Yes.
So that's the other problem. This map is no longer well defined.
Yeah. So if you want to try and do these things for a weak Cartan, it's not even if you know your intermediate algebra is weak Cartan, it's not clear that is coming from the same groupoid structure. So yeah, I've thought about this a little bit and stopped early on because I was running into exactly these problems you mentioned. Yeah.
Right. Thanks very much. I won't take up more of your time that way.
I wanted to take up on Jono's first question. Maybe you already answered it, what I'm going to answer, but forgive me if I make you repeat yourself. But so I understand you have counterexamples in which this correspondence breaks down if condition 2 is not satisfied, right? But do you have a proof that if the correspondence holds, then the isotropy cannot be more than Z not 2?
Yeah. Yeah, this is if and only if you have an element with too much isotropy, you can find an intermediate algebra which doesn't work.
Okay.
Yeah, no, we have that proof.
Yeah. Okay.
Yeah, no, I should have said this is if and only if.
Okay. Thank you very much. Okay, are there any more questions? So if not, I will stop the recording here.